Hello everyone, I'm here. Today I'm pleased to be here to share with you some interesting results about evaluating structural safety of just using machine learning. First of all, let me introduce myself. My name is Nguyễn Trần Hiếu. Currently, I'm a PhD student at National University of Civil Engineering. I'm come from Vietnam. My research focuses on application of evolutionary algorithm and machine learning for optimizing steel structure. This is the outline of my presentation. Firstly, I would like to introduce the reason and the purpose of the research. Section 2 presents the machine learning-based framework for safety classification of justice. In the third part, three powerful classification algorithms are briefly introduced. The fourth part conducts a comparison on the performance of three algorithms when assess the safety of three benchmark problems. Finally, some conclusions are summarized. So now let's start. As you know, assessing the safety of an existing structure is a commonly problem. In practice, for example, many construction after a long period of use has been seriously degraded. Safety assessment is a key factor in deciding whether to rehabilitate or demolish their construction. A second example might be a steel structure exposed to a corrosive environment need to be regularly checked. The structure safety due to the development approach. For one more example, a structure subject to an extreme impact, such as seismic load, fire load, or blade loss, should be evaluate the safety state before continuing use. The traditional safety assessment of structural element is often investigated based on experimental tests or numerical simulation. It can be accurately evaluate the safety of structure, but very time consuming. In some cases, there is a need for a model that can be rapidly predict the safety state of structure in order to promptly evacuate people from the whole structure if it is unsafe. After that, the structure still need to be exactly rechecked by engineer. In some cases, there is a need for a model that can rapidly predict the safety state of structure in order to evaluate people from the whole structure if it is unsafe. After that, the structure still need to be exactly rechecked by engineer. The output of the model is a prediction of whether the structure is safe or unsafe. This is a kind of binary classification problem, and it can be solved by machine learning algorithm. So as you can see here, this is the overview of machine learning algorithm. Obviously, deep neural network like convolution neural network, recurrent neural network outperform conventional machine learning algorithm on unstructured data due to their automatic feature extraction capability. However, they don't work well on tabular data. For such kind of data, the conventional machine learning algorithm, for example, decision tree, support vector machine are good choice. Recently, ensemble methods have been particularly preferred. The concept of ensemble method is to create a strong classifier from several weak classifiers. Some commonly used ensemble method are random forest, extreme gradient boosting, gradient tree boosting. Among ensemble methods, AdaBoost is known as one of most powerful boosting algorithm for binary classification. So, this paper aims to investigate the capability of the ensemble method AdaBoost in evaluating the safety of just structure. For this purpose, the performance of AdaBoost is compared with two popular classification algorithms, artificial neural network and support vector machine, in terms of the accuracy and the area under the ROC curve. The comparison is conducted on three well-known just structures of 10 bar, 35 bar, and 47 bar. Additionally, an investigation on the influence of the parameter on the performance of the AdaBoost model is only carried out. So, as you can see here, this is the framework for safety classification of just the main characteristic of just structure are member sectional area and their value are used as input of the machine learning model. The output is a safety state of structure. The input of training data are generated using a sampling method, which is the Latin hypercap sampling. In this paper, the cross-sectional area that have just been created are assigned to just member, and the structure is then analyzed using the finite element method. Based on the results obtained from the structure analysis, design constraints are checked. If all constraints are satisfied, this structure is safe. Otherwise, if any constraint is violated, this structure is considered unsafe. Input and output are also saved into the database. Once sufficient data has been collected, the training process begins. If the accuracy of the trained model when verifying on the testing dataset is acceptable, this machine learning model is ready to use. So in the third section, three powerful classification algorithms are present. First of all, this is the support vector machine. This algorithm was initially developed for some binary classification problem. For separating data, the best hyperplane is found by maximizing the merging between it and the support vector, as shown in figure 6. As a kernel function such as sigmoid kernel, polynomial kernel, and radial basic function kernel can be used to separate nonlinear data. The second classification algorithm used in this study is artificial neural network. The first neural network model that were introduced in 1958 contain only three layers: an input layer, a hidden layer, and an output layer. Each layer has some neutral where the activation function is attached to mimic the nonlinear data. The state-of-the-art neural network have more than one hidden layer that allow learning extremely complex data. Figure 7 presents a typical architecture of an artificial neural network model with multiple hidden layers. And the final classification model used in this study is adaptive boosting or AdaBoost. The base classifier used in the AdaBoost model is a decision tree. However, a deep decision tree can be overfit on the specific data set. To overcome this problem, the AdaBoost model uses several shallow decision trees, which are sequentially trained by the weighted data. Each decision tree is assigned a weight based on its accuracy. The final prediction is determined using the weighted majority voting method. The illustration of the AdaBoost is shown in figure 8. So, three benchmark problems considered in this study. The first problem is the 10 batches. The second problem is 25 batches, and the final problem is 47 batches. So for each problem, two different data sets are generated. The first data set is the training data set, and the second one is the testing data set. The distribution of safe and unsafe sample in the training and the testing data set are shown in figure 10. Machine learning model for evaluating the safety of church structure are developed based on open source library scikit-learn. There are three numerical examples and three classification algorithms used in this work. So a total of 9 models are developed. The hyperparameter tuning of machine learning model is conducted by combining the research method and the k-fold cross validation. The training dataset is divided into 5 parts, in which 4 parts are used to train and the remaining one is used to validate. The obtained values are summarized in table 1. After finding the hyperparameter, the full training dataset are fed into the machine learning model. When the training process is complete, the model are ready to predict the structural safety state of the testing dataset. And two metrics are used in this experiment. The first metric is the accuracy, and the second one is the area under IOC curve. A problem is carried out 30 times, and the average accuracy of 3 machine learning algorithms are summarized in table 2. It can be seen that for two problems of 10 batches and 35 batches on 3 algorithms achieve high accuracy over 90%, particularly for the 47 batches problem. The accuracy of the support vector machine and the artificial neural network model are quite low, below 70%, while the AdaBoost model still retains a high accuracy, about 97%. Figure 11 shows the typical IOC curve of the machine learning algorithm for 3 examples. There is a good agreement when comparing 3 algorithms in terms of the accuracy and the area under IOC curve. In more detail, on support vector machine, artificial neural network, and AdaBoost obtain area under IOC curve close to 1 for the first two problems. However, the support vector machine and the artificial neural network obtain area under IOC curve of 0.69, while the AdaBoost model achieve area under curve approximately 0.99 when classifying on the 47 batches testing dataset. To investigate the influence of the training dataset amount, 7 training datasets of the 47 batches problem are generated. The number of samples of 7 datasets are 100, 250, 500, 1000, 2500, 5000, and 10,000 respectively. The amount of the testing dataset remain 1,000 samples. The accuracy of 7 AdaBoost models are shown in figure 12. It can be observed that the accuracy of the classification model significantly improved when increasing the number of samples from 100 to 250, while augmenting the training dataset to 500 sample, the accuracy achieved 0.933. The accuracy for generally the number of 1000 sample is a good choice when balancing the accuracy and the quantity of the training data. An important key factor of an ensemble model is the number of Bayes classifier used in this model. In this study, 6 adabus models are compared where the number of Bayes classifier are 5, 10, 50, 100, 500, and 1000 respectively. The model are trained by the same 47 bar training dataset of 1000 samples. The prediction results are present in figure 13. It can be clearly seen that the accuracy of the Adabus model is greatly enhanced when extending the number of Bayes classifiers from 5 to 50. However, when increasing the number of Bayes classifiers from 50 to 1000, the model quality does not improve. Finally, some conclusions are summarized and follow. In this study, three machine learning algorithms, including support vector machine, artificial neural network, and AdaBoost, are used to identify the safety state of just structure. The results of the present work demonstrate the potential application of machine learning for structure safety evaluation. For small-scale structure with few input features, only algorithm achieve high accuracy. However, for large-scale structure having many input features, the Adabut algorithm exhibit a strong ability in comparison with other algorithms. And an investigation on the influence of the training dataset size and the number of Bayes classifier implemented. The results of the investigation provide a good suggestion when developing machine learning model later. So this is a short presentation of our work. Thank you for your attention.